Hi everybody, thanks for being awake. My name is Barrera. I will present the result that we have carried out for interacting galaxies in the Khalifa and Manga surveys. First, let me start with something that Sarah said in her talk before, and it's the fact that if you want to study the impact of interactions in galaxy evolution, you require a large sample of galaxies. And the reason that you require a large sample of interacting galaxies is that when you look at only a galaxy like this one, you wouldn't have a snapshot of what is going on. So you would require a large sample of galaxies that cover different stages of interaction, different mass ratios, different separations, so you can really understand what is going on. And even more, if you want to quantify this, you will require a sample of control galaxies, so you can say how much or what is the effect of the interaction in the properties of the galaxies, and what can you quantify if it's affecting by interaction or by other circular processes. So just let me give you a little bit review of what has been done using single fiber spectroscopy. In other words, what Sarah has been doing with the Sloan sample. What I show you here is the star formation change of interacting galaxies as the projected separation. So what they found, what Sarah and her collaborators found, is that as the galaxies get closer, the star formation of interacting galaxies get larger in comparison with the sample of control galaxies. Similarly, if you measure the metallicity in the central aperture of the Sloan fiber, you will find out that as the galaxies get closer, the metallicity in the central region gets diluted. So the scenario here is that due to the gravitational forces between the two galaxies, material from the outskirts of the galaxies goes to the central region, and this is causing these two effects: the star enhancement in the star formation, but also this dilution in the metallicity. So with this idea in mind, as you can see here, well, we're dealing with single fiber spectroscopy, but what we really would like to do is study how this process change, because as you can see here, there is a lot of complex things going on in the galaxy at different scales. So we want to study this in a statistical way, and that's why we need IFU data. So first, I will show you the results from the Khalifa survey. You have heard a lot about the Khalifa survey, but the only thing that I want to point it out in regards to these studies is that this is the first effort for a large survey of IFU data that covers a wide range of Hubble types. And this translates that we can not only observe galaxies at different interaction stages, but we also can able to observe homogeneously a sample of non-interacting galaxies. And this is really important. So you can do several things. For example, you can study the kinematic misalignment between the stars and the gas. We have found that for the interacting galaxies, we preferentially see the largest kinematics in the early type galaxies. You can start plotting with different properties, for example, the stellar mass. And well, yeah, we have presented this for a sample of non-interacting galaxies, as I said before, and a sample of interacting galaxies. We can further, we can study the properties that I just described before, namely the star formation and the metallicity. For the star formation rate, we use the equivalent width of H alpha, so the specific star formation rate will be the proxy. And for the metallicity, we use the flux ratios of emission in order to have proxies of calibrators for metallicity. And as I said before, now we can study the properties, how these properties change at different apertures, and compare between interacting and the control sample. So this is what we've done. So what I show you here in the left panel is the equivalent width on both panels is the equivalent width for which is a proxy for the specific star formation rate. And in the left panel, what I show you here is the equivalent width for the central aperture. And again for the control and interacting sample. So this is the control, this is the interacting sample. And what you can find here is that there is indeed a large equivalent width for interacting galaxies in the central region here. But if you go and you take a larger aperture and you say the same exercise, what you find is that you have similar distribution for the control and the interacting samples. So what we're finding here is indeed that is an enhancement in the star formation rate when you consider central apertures. We can study the metallicity or the change in metallicity for interacting galaxies and control galaxies. But more than that, what we do here is study the deviation from the mass metallicity relation for these two samples. As you can see here, the control sample is there is basically no deviation from this relation. And for the interacting galaxies, it's also similar. And this is surprising in the sense that, as I showed you before, we were expecting to have lower metallicity for the interacting galaxies. So we can study this further and start to ask ourselves how they change if we start to using larger apertures. So this is the thing that we did. So what I show you here is in the y-axis is the difference between the median metallicity for control galaxies versus the median metallicity for interacting galaxies at different aperture size. And the different symbols represent different oxygen calibrators. And my point here is that no matter the calibrator that you use, you have either similar metallicity between the two samples or even a slightly large metallicity. And if you start to taking larger apertures, you will have some sort of let's say dilution. Also, for this, the marine metal calibrator is rather similar, close to zero. And if you choose another metallicity calibrator, like for example the you will be able to find difference in metallicity similar to those that has been observed in single fiber spectroscopy. So the point here is that I want to make is that yes, we think that the main parameter that enhances the star formation is inflows, but when we measure the metallicity in the central regions, we also have to take into account that other processes could be induced this similar metallicity between the two samples. And this also, just to mention, this also has been observed in numerical simulation, for example, by Bolton, who is also present here. So moving gears also, we are also trying to study the interacting galaxies in the manga survey. You have heard today and previous days about the manga survey. I just want to point it out that this is going to be tenfold that has been observed by Khalifa, going to be 10,000 galaxies. There have been already observed 1,400 galaxies, and they have been already analyzed. So we can start to play this game of studying interacting galaxies. So in fact, we have done that. Along with a group of China and Taiwan, we have selected a sample of interacting galaxies in MPL4. We have 240 pairs of interacting galaxies. We try to cover again different stages of interaction from pairs, close pairs, and really interacting galaxies. And we also try to understand the properties, the result properties of the interacting galaxies with respect to a sample of control galaxies. So this is the work in progress that we have done so far. So this is what I show you here is a given galaxy interaction or pairs of galaxies. This is the property of the galaxy, different properties like the surface mass density, the star formation rate, the specific star formation rate, and the metallicity. So this is the red represent the interacting galaxy, whereas all these gray lines represent the control sample that was taken by stellar mass, total stellar mass. So we can start playing this game for different galaxies outside different interaction stages and to compare with different control samples. So just to conclude, just to mention that we have learned a lot from IFU data. We have understand that the star formation rate in the central region of galaxies is enhanced. But you can also see that moderately suppressed in other regions. This is also in agreement with numerical simulations, for example, from Jorge Moreno collaborators. We find similar metallicity, suggesting that there is that stellar or AGM feedback may also play a significant role when you measure the metallicity in this galaxy. And finally, the IFU surveys, at least nice place to study how this complex process it transforms the properties of galaxies and the impact in galaxy evolution. Thank you very much.
Thank you, Jorge. Questions? Yes, please. Ruby and here. Could you go back to the plot showing the magnitude difference using two different calibrations for the Khalifa sample?
Yeah.
Are these terms shifted artificially, or is I think not?
No, this is what we measure. So this is actually what we measure for the different apertures. And
right, but isn't that saying that the two magnetic indicators giving you completely different conclusions?
Yes. Yes. No, but the point here is that, I mean, depending on the calibrator that you're using, you can find the value that you have been observing for single fiber spectroscopy. So this calibrator here is telling you that you don't find a strong difference between the control and the interacting sample, no matter what aperture you're taking. Whereas this calibrator is telling you that yes, you may have some dilution in metallicity, and for a given aperture, you will find similar as those presented by single fiber spectroscopy. But again, the point that I want to make here is specific for the central region. And that's the point that regardless of the calibrator that you're using, you have similar or large metallicities for the interacting galaxy in comparison with control nodes.
Yeah, just different calibration. We don't understand the calibration, so I can't pass either of those. Lisa?
Yeah, I won't go into the Mendoza calibration stuff because I'll probably do that much more, I think. But now with Mendoza ingredients, I think you have to watch out for what stages the galaxies are in, because at first close passage, the model suggests that the gas falls in down the spiral arms and then it would go into central Mendoza, but only in a small region, 1 parsec, for example. And then the star formation that's induced then enriches that gas in the center. And then at final coalescence, there's another phase at which the gas falls in again, dilating central metallicity, but then whether the gas in the center is then enriched depends on how much winds there are. So it's quite complicated. So I think it's really difficult unless you're actually separating the sample into the different merger classes, different merger stages, or you've got an age sequence or ranking. I think it's difficult to make a blanket statement about whether there's value.
I mean, this sample in particular, I don't think I mentioned in the title here, but this is only for star-forming galaxies, and these galaxies, when you have the look of the interaction stage, is basically pairs of galaxies or galaxies in close pairs, signatures of interaction. So that's something that MACA can bring you, that you can study not only different stages of interaction statistically speaking. So you can really study not only pairs of galaxies, but merging galaxies with a large sample.
Yeah, we're doing the same as well.
Yeah.
Another question? In the meantime, I have anyone?
Daniel Thomas. The manga results you were going over very quickly. Was there an offset in metallicity? That's what I thought to see.
Well, you can have, this is work in progress. So you can have similar metallicities. You can have similar metallicities. Those are the contour galaxies. You can have this difference in metallicity. So it really depends. And we're trying to quantify this in a more clever way, to see if there is an actual dilution in metallicity or what depends on the metallicity.
Right, so they said you do that. But you generally have an increase in star formation rate. That seems to be.
Yeah, that seems to be the case, yes.
Okay, let's thank Jorge again.